So I think I'm just gonna go over some of these problems that were germane to what we'll do on Wednesday. Put some of the solutions up and then we'll move forward. So going all the way back to homework 5. Yeah, okay, so yeah, these were interesting because, you know, we have this formalism. In fact, let's divide by hand. So if we have the driven undamped oscillator, T over M, we have this interesting formalism that allowed us to get the complete and exact solution, and that was where C is equal to X dot plus I omega naught X. So I'll put the, so that what we're actually looking for is the imaginary part of C divided by omega naught, just by construction. And then we have for this complex quantity, E to the I omega naught T integral over M E to the minus I omega naught T prime plus a C sub 0 that we never bother with. Okay? We never bother with. So let's put the solutions up here for the two problems that we had looked at. So the first one, F of T was C times T, just a constant force growing linearly in time, and we end up with C over M omega naught cubed minus sine omega naught T. So that's after all is said and done. And you know, you might have had C over M omega naught squared times T, but factoring it out this way gives you the dimensionless quantities in the parentheses there. The other one was the driven oscillator. F of T was F naught cos. And this one had some interesting consequences that I'm going to go over. So F of naught cos omega T. And so this is the driving frequency as opposed to this being the natural frequency of the oscillating system. And we end up with the following. This one is a little bit tedious. 2m omega naught cos omega naught t minus cos omega t over omega minus omega naught plus cos omega t minus cos naught t over omega plus omega naught. And that can be simplified or expressed similar but related ways. So this one was interesting because you can't just look at it and know that it's true. You have to be careful that you did everything right. But the limit, we were interested in a couple of things. The limit of x of t as omega goes to omega naught. So if you're driving it at its natural frequency, you can use L'Hopital's rule on this. You end up with f naught over 2m omega naught t sine omega naught t, and yeah, over 1 for what it's worth. Okay. Here you could have also had f naught over 2m omega naught squared omega naught t if you wanted, just to keep that part dimensionless. But even this one you can't just tell that it's true or not. But there is one interesting limit here and that is the t goes to 0 limit. So the initial condition was at rest. So what happens to an object that you given a force, a constant force? So at t equals 0, the cosine omega t is 1, right? So at t equals 0, you're just hitting it with a force F naught. And what happens to an object that you drive like that? Well, you can take the limit here, limit as t goes to 0, x of t, and then you're going to have the t here, or let's just write t small. T go, we don't want literally small times small t. So we just take the linear approximation to the sign, right? So we end up with, I'll write it this way in a nice suggestive form, 1/2 f naught over m. And what do we have? Omega t cancels the omega, we get t squared. And what does that remind us of? No way. T squared was the t squared law. What's 1/2 a t squared? See, f naught over m is an acceleration. So the thing is accelerating just as a body subject to a constant force. Very briefly, see, that's 1/2 f naught over m is an acceleration times t squared. It's 1/2 a t squared, which you recognize as just how something moves under initial constant force. So anyway, that's a nice example. There's a lot going on here. This was the resonance catastrophe, right? The growing linearly in time, and then, you know, to check the whole thing, you see what happened for small t. Okay, good. So all of these, if you just very faithfully do these integrations, nothing can go wrong. Right? You just treat the complex numbers like numbers, and we just had exponential functions. So there really wasn't anything difficult here. It was just a number of steps to get there. Remember, we did that one in recitation, Thomas, right? And you didn't have it written down quite right, but we had done it at the board. So
I know what I did wrong.
yeah, but you may have turned that in before we did the recitation or something.
I think that's what it was.
Exactly. No problem. That's a good problem. Okay, good. So that's a certain skill we're interested in continuing with. So what else we had? Let's see if I have all my concepts here. Right, actually, yeah, building on this is the linear differential equations. We had m r double dot q e plus q v cross b, and this will be set up and took all the way. In fact, I better consult my sources on this one. Yeah. So this one, we actually specified that we're going to have x, y, z coming out the board. We said E was equal to Q, E, J hat, B was equal to E, K hat, and then we suppressed the third of these, and we ended up with x double dot was equal to Q over M. I'm just going to write down what we have there. B y dot y second derivative was Q E so Q over M, B over M, x dot. Good, and then z double dot was equal to 0, etc. So we just suppressed all mention of the z motion. That would have just been trivial. Okay. But as far as working these coupled linear differential equations, what we did was take another derivative here. Okay, so 3 derivatives, which got rid of this constant here, minus QB over M. 2 derivatives. And then we were able to plug equals minus, okay. Equals minus, we were able to plug this one in so that x second derivative gives us QB over N squared y first derivative, so it's equal minus QB over M squared y dot. Okay. So this one we want to look at again. I've made this point before, but I'm going to look at it in this way: d squared dt squared y dot equals minus QB over M squared y dot. Okay. And if you just give this another name, you have the differential equation of the harmonic oscillator. So you always want to recognize that, because once you've solved this a few times, you're justified in just taking that thing and writing the answer down. Okay? So if you wanted to give this another name, here, I'll go ahead and erase. Let's board here. Yeah. So you could say I've got d squared c dt squared equals minus omega squared c. Okay, you just gave things a different name. This is of course y dot, so you're not done by a long shot. But once you have this, you can immediately go off to say c of t is equal to, I gotta choose my letters, a cos omega t plus c. Right, b and e are taken, but plus c sine omega t. You immediately write that down without further ado, because you have constants, you have the second derivative, you have dynamical variable. Okay. And with, but of course this was y dot, right? This time derivative, so you're not done yet. Okay. But that's how you just pursue this problem, and if you have enough patience on it, everything will come out in the end. Okay. Then you still have this different, so now you have y dot, right? And you can drop this. So I will, and then you can just integrate it to get y of t, and if you integrate it, you're going to get another constant. Okay. So you have to start racking up new constants, FGH. And then the second derivative of x is also related to this function already. So if you just systematically integrate these and then take into account your initial conditions, I'll write down what we end up getting at the very end. Let's see, what form is best. So you have several more steps to do. I'm gonna go ahead and write it this way. This isn't the final form, but the omega's already been defined, right? Yeah, this is QB over M. So you can always plug that in if you want, but 1 minus cos omega t. This is a good form to have it in, because then you recognize this. And the x of t will also have this e over omega b, but you'll have omega t minus sine omega t. Now again, since the omega is this QB over M, you can plug that in there and then get the entire, get the thing clear just in terms of the original quantities, QBEM. But this way is also, is maybe preferable in a sense, but if you just keep these definitions in hand, because then you see what's your radius, right? Remember the radius, the R, is in terms of E, omega, and B. And by implication, actually, an E, B, Q, and M are all in there. And then, yeah, you recognize this was the cycloid. So we could do a simpler version of this problem, something like that on the exam as well, where once you get this down here, you can start making, significant progress on it. Just by because at this point it was all antiderivatives. And all of your constants that you were racking up here, A, C, there were a couple more that came into play. They could be determined by checking your initial conditions. So our initial conditions were we were at rest at time equals 0 at the origin. Okay? And that was enough to determine everything. Okay, so that one was pretty fun. Anything else to say about that one? Not for the moment. So, actually, we could be back on this cycloidal discussion for a moment. Let's see. Because we've done the length of the cycloid, we had that as a solution of the motion. Somewhere I had the problem. Wouldn't we have the problem with the frequency of oscillations in the cycloid, in the base of it, the minimum of the cycloid? Must be this one. Oh yeah, it is. So small oscillations inside the inverted cycloid. So yeah, let's look at that one as well. You see, all of these things are tied together with the theory of small oscillations, right? The harmonic oscillator, theory of small oscillations. So let's look at that in a different form. So in the inverted cycloid, this one was a bit tricky. So in the inverted cycloid, so we have to give it a length. So minus 2r, and this is x, y-axis, so this is 2 pi r, and this is pi times r. So we don't have this thing as a function y of x, but rather we have it as a parametrization. So we have x equals r theta minus r sine theta, y is equal to r cos theta minus r. So that's the inverted cycloid, and here theta is a function of t. We'll see more of this next semester, as a matter of fact. Okay, so theta is a function of t, and we're saying, suppose we have something sliding around in here. And if it's sliding around the base, we can imagine around the minimum, it's sliding back and forth with small oscillations. So what we're looking for is, I'm gonna get us a new variable. We're looking for this form, 1/2 m z dot squared plus 1/2 k z squared equals e. Does everybody recognize that as kinetic plus potential energy of the harmonic oscillator, of a mass on a spring of spring constant K, right? But anything that's doing small oscillations is going to have that form. Okay? So that's what this problem was about. So we want this form, because again, just like with this, we could immediately cut to the chase and write cosine plus sine omega t. When we have something of this form, then we can immediately say omega squared is equal to k over m, right? Because we've solved that numerous times, and also, you know, that's the motion in the u of c equals 1/2 kc squared potential well, right? So this is a whole complex of ideas that we have more or less mastered. You know, we've even taken this thing and done the quadrature on it and found the cosine omega t function out of that as well. Yeah. So yeah, what does that have to do with this one? So now we have a mass that's sloshing around the bottom here, and we have to find the kinetic energy, 1/2 m x dot squared plus y dot squared. And since we've done that, let's remind ourselves that's 1/2 m 2, and we're going to keep that 2 there, by the way. That 2, so we have 1/2 m 2 r squared 1 minus cos theta dot squared. And here I'm going to draw an arrow. Well, no, I'm going to draw an arrow there. Draw an arrow right here. What that turns into for theta very close to pi, which is near that minimum there, what that turns into is 1/2 m 2r squared. This 1 minus cos pi turns into 1 minus -1, which is 2 as well, times 2 times theta dot squared. And what we've then found, and when we do Lagrangian mechanics next semester, we'll do a more rigorous introduction to this. But what we've found here is the substitution for m, right? The substitution for m is what's in the red parentheses. So that's the idea there. Now the potential energy, for the potential energy we want, clear up some space over here. But this is just an extension of our expansion. Remember the k was the second derivative, so what we need is u of theta equals u of pi plus u prime of pi theta minus pi. This one's going to vanish, of course, plus 1/2 u double prime evaluated at pi theta minus pi squared. So that's just the Taylor, the quadratic expansion. And this one is irrelevant because it's a constant. This one is 0. So we're looking for u of theta equals mg. And then the second derivative of this thing here, I'll write it this way. We're looking for u of theta 1/2 something theta minus pi squared. And there's that second derivative there. And what you end up with, since you're just taking derivatives of this, you're getting, minus sign and then minus cosine, but cosine of pi is, so you're just gonna get mgr. mgr, okay, theta minus pi squared. So here's what our new energy expression looks like. Oh, and one more thing, and then we're just gonna let phi equal theta minus pi, phi dot is equal to theta dot. So then we've transformed this problem into this 1/2, and I'm gonna put my red parentheses here, 4mr squared. That'll work. Phi dot squared plus 1/2 mgr phi squared is equal to E. So yeah, I had set this one up in class, most of the steps here, but this is a really good one. Because really what we were just doing is expanding this thing, but we didn't just have some M. So at this point, we should just be able to read this off with some red parentheses again. Right? There's our M, there's our K. So that's omega squared, which we're used to calling K over M, in this case, it's mgr divided by 4mr squared. And this is an interesting result, G over 4r. So it has the frequency of oscillation of a pendulum of length 4r. We'll study that more next semester. Because that 4r is actually not a, I'll even show you what we're going to prove next semester. If you continue that cycloid out this way, and you guys remember the length of the thing was 8r. So if you build a pendulum like this, and Huygens, I think, came up with this idea, if you build a pendulum of length 4r, and we'll prove it next semester, you release it from here, and it wraps around these cycloidal, these actually come in vertically, right? It's a cusp. Wraps around there, then this thing will be amplitude independent. This is a way to build a pendulum that has an amplitude independent period, which the ordinary pendulum doesn't have. So yeah, there's a lot going on here. We'll do that next semester. But for now, we just want to recognize things that have this form, because if they have that form, we're done. Right? It has the same form as what I had up here, different letters. Good. That's an important theme going through that. A lot of problems, you bring them into a form that of something you're really solving. That's something that happens quite a bit. And you can just inherit all your old results. Okay, good. So what else we have of importance is the central force. We'll definitely put some central force themed problems on the exam. So here we just have to be, what I have in store for us up there. Yeah, we just have to be prepared to deal with fundamentally this thing. Unit vector, okay. With or without the plane polar coordinates formalism. So the one example where we did use plane polar coordinates was the, well, the general case. I'll just say, you know, in both cases, u of r is equal to minus integral f of r prime dr prime a to r. So yeah, if you're given a central force, you should be immediately ready to get the corresponding potential energy, and in that case, you can then derive actually, I'm skipping a step or two here, right? But you remember, there's a progression from here down to here, this via the plane polar coordinates, okay? And the conservation of angular momentum. So, yeah, from this we did R vector is equal to R hat, et cetera, all this, right, et cetera, the plane polar coordinates. And then we had L is equal to R cross and R dot. And because that was constant, that allowed us to go into this formula of plane polar coordinates. But the other example we just did was kind of the opposite order. We just wrote down this one here, A cos omega t, D sine omega t 0. And then by taking two derivatives, we discovered that mr second derivative is equal to minus omega squared r. Oh. By taking two derivatives minus m omega squared r. And because of that, we were able to declare that as a central force. Okay. We didn't know by writing it down. Here, what we knew was, okay, this is just something that's tracing out an ellipse, right? But by taking two derivatives and showing this, then we realized, okay, that must be a central force minus m omega squared r multiplying divided by the same thing. And at that point, this is, well, including the minus sign, this is your f of r, and you could get u of r is 1/2 kr squared. Okay, so yeah, we want to, and you know, if you're given one of this type, you don't want to confuse it with the plane polar coordinates, right? If you have it in this form, this is a Cartesian coordinate triple, right? Order triple, x, y, and z. So yeah, I won't try to fool you though. So if we have a problem like that, I'll probably draw attention to it. Either way. So let me see what else in the central force. So yeah, we can do various things. Oh, very important here. This effective potential, yeah, I almost forgot. So you've got that effective potential, and the whole meaning here is that it's effectively a one-dimensional problem, and you can just use all of your one-dimensional dynamic skills on it. And in particular, the effective potential of different kinds. This one for 1/2 k r squared, you know, looks like that. Has a local minimum, circular orbits, has a second derivative. So I'm just going to write omega sub r squared, second derivative at r0 divided by m. Just small oscillations theory. So again, this was a case where we had this form here, and we can immediately write down the answers. And in fact, you know, you could say r of t equals, maybe we should, and we could say it's r naught plus some constant cos omega sub r t plus something else. If you just want to write that down, or you can just say, yeah, this is a small oscillation problem. That's what's going on. We never did, I didn't write that down, did I, in class before? Should have. It was implied, right? It was always implied. In other words, what we have is small oscillations about r naught. Small quantities r minus r naught, which is just some constant cos omega rt. And the lesson is, once you see this form, you can just go to those conclusions. And, you know, whatever else has to be said about it. So, good, this is perfect timing. That brings us to the apsidal angle calculation. So the apsidal angle, once again, it's the angle swept out between R min and R max on a nearly circular orbit. So yeah, you sweep out this much angle. For the Kepler problem, of course, it's pi, but it doesn't have to be pi. And we have this formula that we derived. You guys should go back and derive this again sometime, just for fun. This one here. It's better than memorizing it. Where R. Here are not the circular orbit is implied. So we had the example of the Newton potential plus this next perturbation that we're starting to learn more about. And, you know, when you write this out, the second derivative and all, it looks like it's going to be pretty bad. But a little bit of arithmetic turns it into, which one had the minus sign in the numerator, the denominator? This one here. I do. Actually, I may not. Absolute angle. Who's got it in front of them? Was it 1 minus or 1 plus 3 beta over alpha r naught squared? Something like that. Anybody see that? I probably wrote it down for one of you guys.
1 plus 3 beta over alpha r squared.
Yeah, okay.
And
1
1
minus. Yeah, I was just trying to remember which one had the plus, which had the minus sign. I know I wrote it down for Eric, but he's not there. Oh, okay, well, that's great. So anyway, it looked like it was gonna be bad, but then we have it, and this was still exact. This was still an exact result. And since, you know, this is a small correction or small deviation from the perfect sphere Newton potential. So we can assume that this is small, and if this thing in parentheses is small, we can expand it. So just give it a name, and I have 1 plus z over 1 minus z to the 1/2 tau. And so what I'm going to do is call that f of 0 plus f prime of 0 times z. That's going to be my linear approximation, which is plenty good. And right up here, my f prime is equal to 1/2 1 plus z over 1 minus z to the minus 1/2 power. And then and that's just going to be a 1 when we're done with it. So the derivative inside is 1 over 1 minus z plus 1 plus z times negative 1 minus z squared times another negative 1. And when we evaluate it, we end up with 1/2. We've got a 1, we've got a 1, and then we're just evaluating it 0. 0 minus times 1, so 1 plus 1. What a great answer, it's just 1. So f prime of 0 is just 1. So for that, so because of that, we can write c is equal to pi times f of 0, which was just a 1, plus 1 times this small quantity 3 beta over alpha r naught squared. Plug that in again. R naught squared. Or, yeah, either way. Or you could write pi plus pi 3 beta over alpha r naught squared. Either way, we see that this is actually maybe better because it's pi plus something small. That's the way we want to look at it. Okay. Plus something small. And this you can hand to the astronomers, or they can hand it to you, or when they're making their observations. And I think I mentioned in class, you've got satellites orbiting Earth that do so many orbits over the course of a year, they're going to collect all kinds of angle here in a nearly circular orbit. Good. So we still don't know how to calculate this beta, but we will. Actually, you can hand this to the astronomers, and then they could come back and tell you what the beta is, and then you could calculate it and maybe learn something about the interior structure of the planet that you're orbiting. Good. So there you have it. Those are all the themes that we'll